Hello, welcome back to the channel. Today we are going to be discussing this paper over here, but first a little bit of motivation. So basically we want to do melody extraction, and we can do that using a Python script. I had attempted to do that in this script right here. I'm not going to type the script from scratch today. I hope to eventually make a tutorial where we type this script from scratch. Or at least not this specific script, but something that extracts the melody. But for today, the script is not ready yet. I'm still working on it. But basically, I can show you one of the things. So there's MIDI util. We import MIDI util, and you'll need to do pip install MIDI util in order to use it, of course. And then we have an on progress callback, completed total. So this is the number of steps completed. This is the number of steps total. What it does is it calculates the percent here, and then it does the line to print, it does that, and then it formats the percent in here. So the 0.1f means to round to the nearest one decimal place. The carriage return \r, that is a control character that will tell the console to actually go back. So like here we don't use print because print will add a new line. But we use sys standard out write, and then the carriage return, and then the line to print. So what it will do is it'll print, and then it'll, for the next progress, it'll go back. So the \r tells it to go back and print again over the previous text. So that's how you do progress. I can show you briefly. So if I run this, see how it's updating the progress without having to print a new line. That's what I'm doing there. Yeah, I'm gonna stop that. I already ran the script earlier. This is just ignore the first one. That was just me playing. The second one, this is the file that I'm reading. Lindsey Sterling violin playing of Phantom of the Opera. And then we have the audio segment. Basically, we read the file as usual, as we did last time. We do this, nothing new. We did this last time. We create a note list for all the notes that we want. Freq list is the frequencies. We convert the notes to frequencies. DT is our time step, of course. And then here I changed things a little bit. 8192 was what I used last time, but it's a slightly bigger value. Just see if that improves the results. Not really much difference here, but really the W step will tell us how much is the window size, and I step is the step size. Well, again, it's not too important. I feel like I'm being too detailed with this, but basically we create a MIDI file. MIDI is our MIDI file. That's how you create a MIDI file. Of course, you have to calculate a tempo as well, which I do here. I won't go into the details of what exactly goes into this today. I hope to do that in a different video. But we put the track name there. You can put whatever you want here. And then the tempo is whatever we calculated. And then here we initialize some values where we're going to use the notes. And so for each of these steps, n step is the number of steps, step is the current step, and we use the I step is the step size, so the number of samples per step times the step number or step index, and that's I0, that's where we start looking at the samples. T0 is that times the DT, so that's in seconds as opposed to samples, and then beat number, we have to divide that by how many samples per beat to have the beat number so that we can write the MIDI file. On progress, we call that here, we give it a step and the number of steps. Okay, we calculate a times array as usual. We've done that in a previous video, so we'll skip that. Phase list, we've done that. Shift factor, done that. Window samples, we've done that in a previous video. Okay, here this part is new because here we are in a loop, and then the very last chunk of samples potentially will have less samples than what we're expecting, so we'll have to break out of the loop at that point so that we don't crash the program. And we don't even care about the last chunk anyway. But here we do our product as usual, the frequency, power spectrum as usual. We've done that. The new part here is I did an approximation actually, so freqpal.argmax. What I did, and this is a little bit bad, it turns out this This is okay, but it won't give us, because when we look at the spectrum here, the power spectrum, we can see that this particular harmonic, this B note, this was the G note that we were looking at the other time. It has a B harmonic that happens to be taller than all the other peaks in this particular scenario, but these peaks actually jump a lot. So we can't rely on the amplitude of the peaks. We'll have to do some math later, and it turns out this is actually the fundamental frequency, but it's okay. So if we use the reasoning that, okay, if the instrument has all the same harmonics for whatever note you play, then it shouldn't matter if the note is a B instead of a G, as long as the progression of the notes stays the same, and as long as this is still the peak all the time. This, what is it? Fundamental, first harmonic, second harmonic, third harmonic, fourth harmonic. As long as the fourth harmonic is the one that's the tallest all the time, we should be okay. And I don't think that's the case all the time, but anyway, just try it just in case anyway. So what this does is take the tallest peak, the argmax will take whatever's tallest, and it'll give us the index into it. So, oops. That's what we're doing here, and then the note itself, we have to go to the note list to look up what's at that index, and then we round it, and that's our note. And then, long story short, here we just write the note. We calculate the duration, basically. If it's still the same note as the previous, we just add a little bit to the duration. Add 1 to the duration, so if the same note appears 5 times, we just want 1 note, but with a duration of 5 beats. Okay, final progress update, and then a final note write, and then we save the MIDI file. Alright, so I ran this earlier today, just so you don't have to wait. It's like 3 minutes to run. I don't want us to be waiting that long, but okay, so let's listen to just a little bit of the original MP3. So you can hear that there is the violin, and there is the piano, and there is the strings, maybe, or whatever that background is. So it's definitely polyphonic. Okay, I'm going to stop it here, but very nice song. Thank you, Lindsay, if you're watching this. Not that Lindsay would want to watch it. So this is our MIDI result. This is the result of the peaks jumping around, because the peak that is the tallest is not always the tallest. The peaks are going to be different. But you can hear that the notes that this is picking up, it is actually staying for the most part on key, at least. So these are mostly within the same key of what the song was. So obviously, as you see, like, okay, if we just take the naive approach of just take the maximum, the argmax. That's what argmax means. We take the tallest peak, and then take the note from there. If we just do that, then we have this jittery, it stays on key, but it is still not quite there. So that is the motivation for looking at something else. And this is where we actually look here at the paper. Alright, so this is a paper by, I believe, a PhD student, but I'm not certain. I'd have to look up the authors again. I don't think this is a paper by a professor. I don't think that, but it might be. I might be mistaken. But yeah, basically what I'm saying is take it with a grain of salt, but it is some good work that they did here, so I do think it is worth looking at. And actually, the reason why we found the paper in the first place is if we go to GitHub and we search for audio to MIDI, one of the results is this one, audio to MIDI. And this is the algorithm. The core algorithm was actually done in this repository. So if we click that, it takes us here. And they have this paper. So if we click here, we find the paper that we are looking at, which is this. So yeah, so I printed it out, but we'll look at the paper copy. What I wanted to point out is we will need this project here. This is the core algorithm. You can use it for predict_on_audio.py is the starting point script that will convert the audio to MIDI. And that one actually relies on something in this GitHub repository, this audio to MIDI. If you go into model over here, then you have these two model files. You will need those unless you want to train the model yourself. Whoops, what am I doing? In which case you don't need them, but that is what you need. All right, so this is the GitHub repository. Basically, you can use this to convert. I haven't actually run this yet, but it should be straightforward. You run predict on audio and then you give it the file path, tell it what to do, and it's supposed to work. But yeah, first of all, the first note that I wanted to point out is the title, a streamlined encoder-decoder architecture for melody extraction. So I understand melody extraction, yes, that's what we want to do. We obviously proved that it's not going to work if you take the naive approach of just argmax. You need something a little bit smarter than that. And these people use an encoder-decoder architecture. And what is encoder-decoder? Honestly, I did not know this until I asked a friend of mine who studied, my friend studied AI, machine learning and AI. And so like, the friend's like, oh yeah, that's a subset of deep learning. And so, okay. So we can actually do a Google search for machine learning versus deep learning. Looks like MathWorks has a video on it. You can watch it. Basically, the gist of it is machine learning is the general umbrella term. And I'm going to close that tab. We're not going to watch the video here. I could probably link the video in the description or in a comment or something if you would like to watch it. Or you can just Google that. I'm sure it'll be the first result. But long story short, deep learning is a little bit more hands-off. You just take you just need a lot more data to train it. Whereas machine learning is a little bit, you have to do a little bit more work yourself, or machine learning in general, not including deep learning. Whereas deep learning, the computer figures out what to do with the data, basically. And then, so let's see, I'm not really sure if I can pronounce these names. I don't even know if this is not even, I know how to read pinyin. Let's see, well, even there, without accent marks, it's difficult to see. So that's Li, and then is this Su or Su? I don't know which accent it takes, but, and then I'll just read this in English, Tsung-Han Hsieh. That's not even English. I don't know what language I'm reading that in. And then Yi-Hsuan Yang, I think. Yeah, okay, so these are, looks like Taiwan. These people are in Taiwan. Okay, their email addresses. And this is from 2019. So relatively recent, like 4 years. Not bad. It's okay. Would have been good to have something more recent, but this is still fairly recent, better than something that's older. Okay, melody extraction and polyphonic, whatever, important. Okay, we know that. In this paper, we proposed a model. Okay, encoder-decoder. Okay, so they use a machine learning, deep learning. Okay, 2 technical contributions. Inspiration. So the pulling indices between pulling and unpulling. Okay, localized melody. Okay, so they use the indices. I'm assuming indices is a concept in deep learning because looking at the code, it's going to be It's just something that they pass. It's not something that they calculate manually, so we'll just take it that way for now. Okay, we can achieve still much fewer layers. Okay, so it's nice that they have a simpler convolutional model. Propose a way to use the bottleneck. Okay, estimate existence of melody. Okay, yeah, that's a good thing they do actually in this paper. They estimate the existence of a melody, not just the melody itself. Use an argmax function instead of, okay, so they use argmax, but they do it on the output of the machine learning model instead of on the spectrum itself. So instead of using thresholding, because thresholding has limitations, and then it looks like their model is effective. Okay, so the abstract basically tells us what their paper is about. And by the way, I forgot to mention this at the beginning, but if you're not looking to understand what this paper does, then feel free to click away from this video, because this video is, I'm not going to write any code in this video. I'll do that in a separate video. So if you're not interested in this paper or the GitHub repository, we'll look at the code there, then feel free to click away. Yeah, okay, so introduction, okay, the fundamental frequency. Basically, this is stuff that we kind of know already. You can read the introduction. It has some ideas here, but basically it says that we can use neural networks. Neural networks have been used before to do this, and then we have t is the time, if it's the frequency, we're trying to estimate the fundamental frequency. And then let's see, there are some promising results, but there are some issues. The second issue, yeah, so basically they bring out some issues and they're like, okay, we are solving this, we're making contributions. Okay, so we'll go on to the second page. Related work is the section where they talk about the previous work that has been done on convolutional neural networks. And in this figure here, they actually say, like, so these are neural networks also, and then this is encoder decoder. So they're kind of taking like, okay, we're doing encoder decoder, but we're adding this. So that's kind of what that is. This is basically background. What's been done before? What new things are we adding? And then the proposed model is where they go over the system. So the convolutional layers, and then that's what they're doing. So this is their schematic of the model. And this is the part that if we go into the repository here, we will come to that in just a moment. But this is the base algorithm. So if we go into predict on audio.py, and this is the entry point, this is the main function. Let's see, do they have, yeah, if name is main, then args parse, and then call main on this stuff. And then main, okay, so main takes the file path, it calculates a model path, so that's the model file that I showed you earlier in this folder with the model. So it needs to read in that. And then the big thing here is this melody extraction function. It either does it on the GPU or CPU, it looks like, yeah. Okay, so this mext comes from here, it's melody extraction, okay. So we need to actually go to melody extraction and find the mext function in there. So if we go to, let's see, what folder is it? MSNet, okay. So we go here, melody extraction, we open that. And here it looks like, okay, so we import CFP process from MSNet CFP, and we import model from MSNet. So, okay, but what we're calling is mext from that code. Mext is going to call CFP process, so it pre-processes the input. And then it's going to create a model. MSNet vocal, MSNet melody. Now what is this? Model is, where does model come from? It comes from here, MSNet model. And by the way, those of you who are very experienced with code, feel free to skip this video as well. I forgot to mention that too. This video is meant for people who are maybe have homework to do this perhaps, and they need a little bit of help understanding the paper. So, okay, what I just clicked on was model because that was what MSNet model, right? Okay, so this is the MSNet folder, and this is the model.py file, that is the model module, okay? Okay, so the import torch, first of all, if we search for PyTorch, oh, okay, I already have it in my history. So if we go to PyTorch, this is a, NN, let's do NN, PyTorch NN. This is the building blocks for creating convolutional layers and things. So basically, to us, and just a heads up, AI is not my background in particular. I studied other stuff. I studied physics and radar signal processing, but I haven't studied AI. So to me, this is also a black box, but that's okay. I can see what it's doing. It's creating a node in the neural network. Okay, and then return indices equals true. So this is the part where the paper talked about indices. It's going to return indices. And then you do this stuff here. Basically create a bunch of nodes. And you can see that, and this one is for melody. There's a very similar thing for vocal. So to us, basically these nodes, they are really talking about the stuff that's over here. Like, so for each of the boxes here, you can see 332 on here, and you can see 332 on here. So, and then 3264 here, and 3264 here. So basically, that's the model. This diagram, this figure shows what they're doing in the model. Okay. So far so good, and then the other thing is when you go in, let's see, this file. Okay, so we create a, where does it do the net? So here you do, if it's vocal, you do the vocal model. If it's melody, then you do the melody model. And then this net variable, it is used later down here. So they do it using an if-else. This could actually have been done without the if-else. They could have just done the batch, but it's okay. They still did a good job. Yeah, that's what you have when you have scientists write code. They don't always write the best code, but their code usually, at least hopefully, works in theory. So that's because if you have software engineers write code, they pay more attention. But it's okay. I'm not saying software engineers are better than scientists or anything like that. No, but it's just something to keep in mind, that you can write better code most often when you see code from scientists. But it's okay, they did a good job, and I'm thankful for the paper. They're very useful. So it looks like they iterate through all the segments. The seg function, so the seg function and then the iseg function. What they are doing here is they're taking the data, which is a big array of all the samples, and then they segment it into a bunch of segments. Seg x is the input from the data, and then seg y is going to be the output. So then batch x is the element from seg x. So they do this frame by frame, basically. And then once they're done, basically they add the predictions, all the predictions to the seg y, and then seg y they desegment it into a big array again. But here they do batch x new access. So we've been using reshape in my videos, and reshape makes more sense to me, but you can use new access if you want. That's another way of saying reshape with a 1 here. And then we do, it takes this numpy array, it puts it into PyTorch. PyTorch is that black box thing that does neural networks for us so that we don't have to. And then if it's on the GPU, it also transfers that to the GPU memory context, which is good, okay. And then this will do the forward function. So the prediction y and the EMB, I don't remember what the EMB was, but this is basically, and also if you're on the GPU, you put it on the CPU again, and you put it into a numpy array again. So that gives you the numpy array back. Okay, let's look at the seg function just to make sure we understand it. So we have seg, and that has Basically, we have the frames length tells us it has a default value of that if you don't provide anything. So it takes the data and it cuts it into a bunch of, yeah, so that's what it's doing here. It cuts it into a bunch of chunks, and then if there's a remaining chunk, then it also appends that and it returns it. And ISEG does the opposite. It just takes and populates this X with all the data that is in segments, but it puts them back into a flat array. So that's what that does. Okay. And then finally, once it's done making all the predictions, it's a flat array again. Then it feeds it to est, and that gives you the est_r, and gives it the center frequency and the time array, which are calculated over here from the CFP process. Okay. And the est does, let's see, so it's est time, output, est freq, argmax. Okay, yeah, so this is where the argmax is that they're talking about. They're talking about, and here they are talking about doing an argmax, but that is of course done after the over here, because in this figure they say that, so we calculate the melody, basically that's the output, and then there's a non-melody estimate that they invert, by the way, and then they concatenate it together with the melody estimate, and this gives it this result. So at the points where there is no melody, the non-melody estimate will be bright, and so the argmax will return the non-melody portion, and that will give you the, basically, you know that there's no melody if that's what it returns. But if there is a melody, then the non-melody portion will be a lot dimmer and the melody will be brighter. So that's what they're doing there. When it calls net over here on this line, that is when it's passing the raw information, slightly processed information actually. It passes it into the neural network, and that's the forward. So when we go to here, this is the forward function. So when it calls the net here, that information is passed into this function, and this function takes this x, it gives it into the conv1, which is over here, conv1, and that takes the result in indices, then it takes that result, passes it into the second one, and takes the result and passes it into the third one. Then it has a bottom layer, and then it takes the result of that, passes it into the up converter, and same thing, and then the output is, okay, this is where it does that. Okay, so the cat, it concats the bottom layer, which is whether it has the melody or not, with the U1, which is the final output. And that we've seen over here. So basically it does all this stuff, and it does the bottom layer as well, and then it concats that. So that's where it does that. So this is the output, and the BM is the bottom layer then. Okay. So if we are looking here, then the estimate is going to be actually, let's go here first. So EMB is, I think, the bottom layer, and pred_y is the output that's concatenated here along the second dimension. Okay, and we have that, and we pass it into the, afterwards we pass that into the est function. So then all it has to do is take the argmax of the output along the 0th axis, and that gives us the estimated frequency, and it puts that into the I guess the estimated frequency is really the just the argmax, and then we have to go into the center frequency array to figure out what the frequency actually is, because these are just indices, and then this is the actual frequencies. And then it concatenates them with, let's see, est time, est freq, axis 1. Oh yeah, looks like it puts the time into one dimension and the frequency into another dimension, and then it returns that. Okay, yeah, so that makes sense. That all makes sense. And then if we go into here, so that's what, oh, I guess not there, here, right? So that's what it does. And then the final thing is CFP process. This one is a little bit tricky because CFP process is the pre-processing. So if we go in here, that's where they talk about the model input. The model can take any audio representation because, of course, the neural network can take any audio. That's what neural networks do. But they do some pre-processing to kind of help with it. So what they do, Z sub S is going to be just the short-term Fourier transform, and then the others are going to be some, I guess, periodicity representations that is supposed to help with multi-pitch. But they use the CFP representation, which is the combined frequency and periodicity. This reference 16, I tried finding this reference because I didn't quite understand what exactly, I mean, because they're doing their own thing in the code, in their code, but I wanted to see what exactly is the CFP that this paper talks about. And there's a paywall for this paper. It's like, I forget, $30, $40, something like that. But it's not the paywall that stops me. It's really the fact that I have to give them my address. Because if I give them my address, my suspicion or my fear is that they will then send me spam or junk mail. Hey, sign up for our journal. Hey, you might be interested in whatever. Yeah, so that's the part. And it's a PDF download. Like if it was they were going to mail the paper to me, I understand, but to give them my address just so I can download a PDF over the internet, that makes zero sense. So I was not able to acquire this paper, 16 from the sources, but it's okay. We'll just work with what we've got. So here they define stuff, and their parameters, high-pass filters, removing the DC, and then DFT activation functions, and we can look in the code. They actually do that there. So if we step into the CFP process function, CFP process comes from MSNet CFP. So CFP.py is over here, and we can look at the situation here. So these are comments. First of all, they just tell us what things are. And then this is the short-term Fourier transform. They give it some information, but let's go to the CFP process function first. So that way we know where we're starting. So it gives it a file path, and then so it loads the audio. And then depending on if it's vocal or melody, it gives it a different, let's see, what's the difference between these two? Oh yeah, the parameters. Yeah, so they use different parameters, which is fine. And then they take the, okay, so feature extraction is what they do. Feature extraction is not absolutely necessary for deep learning, but they do it. It's more efficient if you do it. So yeah, that's what they do, and they can concatenate the arrays there. So the main part of this is the feature extraction, and you can find that function over here. And then just so we know what the parameters are, it gives it the Y, which is the audio samples. SR is the sample rate. Hop is going to be our, we'll see what that is in just a moment. And then hop, start freak, stop freak. So it gives that and num per octave. Okay, so let's go feature extraction. We have, so it gives us the audio samples and the sample rate. FS is the sample rate, hop is something else. Okay, so window size is window. Okay, and that's 2049 by default. And then hop is passed on. So we'll see what that is in just a moment. Start freak and stop freak. So the thing here is, this is a frequency, let's see. What are those parameters? And then G. G is going to be the gamma. None of these are 0. They have an if statement up there that compares if it's 0 or not. I don't know why, because none of these are 0, but that's okay. So CFP filter bank is kind of the main processing function of this. Now load audio, just so we know what it is. It looks like we have, so either way, X and FS. X is going to be our data samples. FS is going to be our sample rate. Then if it wants mono, this is a parameter, it's true by default. They leave it at the default. So if the sound is stereo, so if the shape, if it's a two-dimensional array, then take the mean. So it looks like they combine the stereo into just mono if the mono is required. And then the sample rate, if the sample rate, then it resamples using a polynomial method of resampling. It resamples it to the sample rate that the argument wants, and then it returns that, and of course converts it to the D-type, the data type that it wants. So oftentimes audio is an integer, usually short, which means signed 16-bit integer, but then they convert it into a float. So that's what that does. And then just to be sure, mono is true when it calls it. So therefore x will be a one-dimensional array, and it will return the sample rate as well. And then it does the short time Fourier transform. It gives it the hop. So FC and TC. Okay, so this is the, let's just look at the comments up here. FC, TC, okay, I guess they didn't leave a comment for that. Okay, well, okay, fine. So they have FC and TC are the two parameters. I believe this is the frequency and time resolution, but I could be wrong. So FR is the, well, they're calling it FR here. CFP filter bank. Okay, it is FR here as well. So FR is the frequency resolution. Okay, good. FS is the sample rate then. Okay. So this is the filter bank, and it does TFR is going to be the output of the short time Fourier transform. And the short time Fourier transform is defined up here. This gives us the data, the frequency resolution, the sample rate, the hop. Okay, now here's where it defines the hop, or uses the hop. Okay, so the time is start with hop. I would have started this at 0. It looks like these people are MATLAB programmers, so they start things with 1, or hop in this case. And they do that here too. They do indices equals something plus 1, and then they take the indices and minus 1. So obviously they're MATLAB programmers, because like, why would you plus 1 if you're going to minus 1? Like in Python, indices start at 0. But you know, they did a good job still. I'm not complaining, I'm just pointing out that, hey, this could be, you know, as you read this code and you try to write your own code, just keep things like that in mind. If something doesn't make sense, do it the way that makes sense. But if you're going to use their model files, then you kind of have to follow somewhat what they did. So this looks like they do the zeros and then the tau. They do, okay, so this is the ceiling when x divided by hop. So this is the number of hops. This number in here is the number of hops in the data set, in the x that you passed in, times the hop. So the number of hops times the hop is basically, that's what they're going up until. Hop is where they start, and hop is how much it goes up by. So t is an array of times. This is not even times, this is a number of samples actually. That's what t is, I think. Well, okay, and hop is the number of, so t is spaced by hop. Yeah, and then we take the sample rate divided by the frequency, or yeah, divided by the frequency resolution. That gives the big N, which is the number of frequency bins. And window size is the length of h. Fair enough, so h is the window. And then frequency is going to be the sample rate times. So it looks like they're calculating what the frequency is, which is fine. That's what you do when you take a Fourier transform. LH is going to be window size, okay, -1. And then T of R is a two-dimensional NumPy array. It's going to be n by t, or n by length of t, rather. So the second dimension is the time bins, and the first dimension is n is the frequency, so the frequency bins. And then we go through the length of t, so that's I column, okay. And that goes, we take the index, so ti is going to be, they're using it to, let's see, what are they doing here? Round, okay, tau, and then, yeah, sometimes if you don't, I would dig into this deeper, but I just don't have time right now to figure out exactly what this particular one does, but we do have a modulus of n plus tau, and of course, just ignore the plus one, it's their MATLAB thing. So that gives us the indices into the what? Into the TFR array. Yeah, so, and then they use the FFT from the SciPy, which is fine, okay. So indices comes from tau, which comes from, oh wait, it has an n, and n is frequencies. Actually, n is the number of frequency bins. And then tau comes from, okay, oh, right, that's what I missed. Okay, but I used ti, yeah, as I said, this tau equation is a little bit difficult. So it's frequency by time, f by t. And actually, I'm curious, if you think you heard a cat, that is correct. There is a cat on my lap. Yeah, let's see if I can show the cat here. Yeah. Yeah, okay, well, back to the paper. Yeah, okay, so they are talking, okay, that makes sense, because they're talking about f by t, and then their code is f by t. So that is good to know, okay. So that's the short time Fourier transform, which is called from here. And then it does the TFR and takes the power. So it looks like they're using the power. But not just the power, they're raising it. They're taking the absolute, and then they're using the gamma value. And the gamma value is, oh, trying to remember where that was defined. Feature, wait, the gamma, yeah, here it is. So it's going to be 0.24 for that first one. Okay. And then it looks like we have TFR and SEPS. I don't really like the name SEPS because it reminds me of sepsis, another word for septicemia, which is a dangerous medical condition. So I'll just say CAPS or something, I don't know. But anyway, so that's what they're doing. Over here, they calculate a short-time Fourier transform, and then they calculate, this part is a little bit tricky to understand as well, and then especially because the number of layers is just 3. It's the size of the gamma. It's going to be just 3, so they could have hard-coded this, but they did a loop anyway, maybe just in case they increase the number of layers later, which is fine. So it looks like every other time, so after they do the short-time Fourier transform and they have the TFR, but they don't have the SEPS yet. So when this is 1, which is the next value, it starts with 1. Then, since it doesn't have the SEPS yet, it takes the TFR, which is Fourier transform, and then does the real value, real part of that. I don't know why they're dividing by square root n, but some sort of normalization probably. It doesn't super matter. I don't think the machine learning will do much about it, but that's okay. And then they do nonlinear function, which is defined over here. And what that does is it's always non-zero. This is the if statement I alluded to earlier. So if g is not 0, it's always non-zero for this particular program. So it looks like they don't like negative values, which they're taking the real component of. I'm not entirely sure. So this is the part, because this is the part I would have liked to have seen the original, or the paper that defines the values that I mentioned here. So this paper, the 16, because they're mentioning 16 here and CFP representation, and then they put these equations here. And so without the original paper, I have no idea what the code is actually supposed to be, so all I have is this. And what they are doing is they're taking the real component, and any value that is below 0, they set it to 0. I'm not sure if this is supposed to be like, instead of the real component, are they supposed to take the absolute value of the complex signal, or yeah, I don't know. It's difficult to tell because this is all I have to look at. And then they do the cutoff. So the cutoff is the part that filters out the DC signal, and they talked about that here too. So when they say that they remove the DC terms, oh, my cat's tail is, hi cat's tail. Okay, so this is, yeah, that's what they're doing. So the cutoff is basically the number of samples that go into the DC term. And it looks like they do the same to the top, and then they raise it to the gamma power. So that's what that does. Okay, so we look here, and it is a nonlinear function. So that's the filter. They're doing some filtering, raise it to the power. So the first time you have the TFR, and then you calculate the steps, and then on the next loop iteration, the GC will be not 1, but well, the remainder will be 0 again, because 2 divided by 2 is, let's say, 1, and the remainder is 0. So you go here, and then they kind of do a similar thing, but they calculate the TFR instead. And then here they do use NumPy FFT instead of SciPy FFT, so that's kind of interesting. And then they combine some things, or I guess they, whatever they're doing, yeah, they trim it a little bit, and then they combine it a little bit later here. So they do here, and then freak to log mapping, freak to log freak, and then I'm not sure what this one does, but these two, freak to log freak, they do, it's also a little bit messy in here, but basically the idea of this is to go from the frequencies when you take a Fourier transform in either NumPy or SciPy. The FFT layer gives you like something different than what we were doing here, because in our code, in that tutorial, the shift factor comes from this phase list, and the phase list comes from the freq list, and the freq list actually comes from the note list. And so we are already doing a nonlinear frequency, nonlinear Fourier transform where the frequencies match the piano keys rather than matching the whatever the FFT does. But they're using SciPy FFT and NumPy FFT, so they have to, but they need a log frequency too, because ours is already a log, because when we go note to freq, that gives us the 2 to the power of whatever that function. So we're already a log frequency where we do that, but they don't do what we do, which is fine. They use a slightly different, they use the FFT normally. I think, in my opinion, ours is more accurate, or just logically speaking, because we actually do the transform using the frequencies that we need, whereas they do the transform using frequencies that they don't need, and then they convert it to the other frequencies, which I'm not really sure. I mean, I suppose if you're constrained on what kind of transforms you can do that, which is fine. But basically they have the log frequency. So after this step, they have basically what we have, which is log frequencies on the x-axis and amplitudes on the y-axis. So at this point, that's what they have. And this is what CFP filter bank returns. And then that is called from feature extraction from here, and then that returns all of those. And then from feature extraction, then this one takes all of these and it concatenates them into this big W thing. So what this big W variable is it has all of these values, and this is the model input. So this is what is going to be fed to the model. So then that's what that is, and it returns W, center frequency, and time. So then when we are in here and call CFP process, so the data is going to be the W. This is the one that has the model input that we just talked about, and then the center frequencies and the time array. And then that's when it feeds it. It obviously instantiates that, and then it feeds it into the model, into the neural network model, and has the prediction. And then the prediction is going to be estimated using this, and that is how it runs. That's me-ext, melody extract. And let's see if we can find me-ext. So str is already the result, and then it just has to save it to a text file, and that's it. Basically, this is the. So this one actually, I'm not sure. I think I might have said that this makes a MIDI file. Looking at this, I don't actually think that that's what it does. It doesn't make a MIDI file. It makes a text file. But the one here, melody extraction. Whoops. What am I doing again? Okay, computer, stop it. But then in here, audio to MIDI. I haven't looked at this file yet, but it does some smoothing and a note map, which is great. Okay, so it does the model also. Okay, so here they bunched a bunch of stuff into. Then they have write MIDI, which, let's see, what MIDI library are they using? Piano roll, I guess. Yeah, okay, so that's what they're using. Piano rolls, okay, so they do that, and then main MSNet, load state predicts, load state dictionary. So this is important. The model path, it loads the state dictionary, and then it runs that way. So this is the one that saves the MIDI. Yeah, but this one does virtually the same thing. You would just have to save it to a MIDI instead of to a text file, which, whoops, where am I looking again? Here, I guess. Yeah, so that's that. This is a little bit about how it works. What I did not cover in this video is the training, which honestly, the training is like, I would have to spend more time looking at this time that I don't have right now. This looks like the train function. What I can tell you so far is they do instantiate a model here, and they get all the center frequencies, I guess. And then what they do is, oh, pickle, right, because you have to prepare. So these pickles, in Python you can use a pickle file, pickle.load and pickle.dump. When you have a variable, like let's just say you instantiate, and it has to be serializable too. It can be a numpy array, but it can't be something that you can't serialize. Serialize means you convert it to a string or a binary buffer or something like that. So, and that's what they do, because they tell you, if you read the README, it tells you to run data arrangement first. And that's what you do. You give it the, so you call main, and then it's going to do, so in the melody case, it is going to look through this function just returns a list of database information, or I guess songs and whatnot. So it pre-processes all the songs, and then it saves it to an array, and then let's see, what does that even do? Basically, it creates some arrays, xlist and ylist, and x is going to be, I believe that x is CSV2ref. Yeah, so that must be, okay, xlist, ylist, yeah. So the idea is, without digging too much into which line of code does exactly what it does is xlist is going to be our, if I'm reading this correctly anyway, xlist.append data. Yeah, so xlist is going to be the audio samples, or I did the, well, CFP process, so it can't be the audio samples, but it is the these values. Once again, we keep coming back to this. So these Z values. That is what xlist is, the pre-processed model input. and it is, when you pre-process it, it actually makes it easier and quicker for the deep learning neural network to learn. So that's better if you're smart about how you feed that data to the neural network. And then YList is the ref array, which it looks like CSV to ref of YPath, which looks like the Melody CSV. So that's basically the answers. XList is the questions, YList is the answers, and then it dumps both using pickle, and then it reads both back using pickle over here. Pickle is very useful. But yeah, the entire idea of, and it looks like X test list, Y test list, the entire idea of training, that's what they're doing here, is, and they're using an Atom optimizer. They mention Atom in here somewhere. Let me see if I can find where they mention Atom. Encoder and decoder. Let's see. We can go in here. Lyrics, datasets. Okay, MedleyDB. Yeah, that's MedleyDB is what they used for this. And then so they have different pinch from. Okay, so that. I'm not seeing it at the moment, but I remember seeing they use an Atom optimizer. So that's what they're talking about. With regards to the implementation, it is, looks like it's really just they import, let's see, Optim. What is Optim? Optim is going to be torch.optim. Okay, so it's part of Torch. So you don't have to write it from scratch. And this goes to show that not everything you even have to write from scratch, especially when you're doing machine learning. You can just use a module. Now, if you're going to port this to some environment that doesn't have the packages, sure, you can write them, but you can prototype still using packages. And then net.train. Then it looks like they're giving it the batch X. So this goes through the data. So it gives it the prediction is batch X, and then loss is the difference between prediction and Y. Loss.backward, optimization.step, train loss. So I'm not entirely familiar with, and this is the non-CUDA version. This is GPU, this is CPU. And then eval. Not entirely familiar with how training works. I know what it does, I just don't know what every line of code does and which variables do specifically what. But what it does is it gives it the values that it loaded, so the X list and the Y list. It gives it the X list rather. And then it uses the Y list as the answer key to train the model that's saying, hey, this is supposed to be the answer. How exactly? Not sure, but that's basically what it's doing. When you give a machine learning model a bunch of questions and a bunch of answers, then eventually the model will give you the answer with you just giving it the question. So that's what machine learning is, and they are using machine learning here. And again, there was like these other papers that they cited use machine learning. Those results are promising, as they said. And then this is their results. So basically, the ones in bold are the best performers. So and ablated is the one without the non-melody detection. So the one that's not ablated is the better one. So, and that's the one that they propose. They only did ablated just so that they could compare and see that, yeah, indeed, the melody detection is necessary, or non-melody detection. So yeah, that's what we're doing. And then MedleyDB, general melody, they did the vocal with 3 databases, but they only used MedleyDB for the general. And I just wanted to go and just make a note about MedleyDB. If you Google that and you go to their homepage, looks like a very useful database, but also what I don't like. And let's see, welcome to the whatever. Okay, trying to figure out where So in order to go, download terms of use and licensing information compiled by whatever, some college people, basically is offered free of charge for non-commercial research use only under the terms of the whatever. So this is what I don't like about this. Now, just to be clear, I don't plan on making any money off MedwayDB or even off the the stuff that I'm making. I do hope to eventually make money with either my YouTube channel or with selling software, because that's what you do. So the thing is, like, the non-commercial research use is like it's viewed as this good thing to be doing, which is great. You can do that, but the thing is, if you are going to improve society by writing software that improves people's lives, you're going to do this very good thing. Well, the thing is, you need time for that, and you need money for that too, because like eventually you're going to run out of time. Like me right now, for instance, I have to go do my day job. I don't have time for this a whole lot. I only have a little bit of time for this YouTube channel and for writing software on my own. It's a challenge, and the thing is, with any, let's just say we start an organization, it's non-profit because we want to look good on paper or whatever, and we don't make any money off of it. We're just like, we're doing this for the good of the public and whatever. Well, guess what? In a couple of years, we're going to go broke. Maybe if we have some sponsors who donate money, but still, you need money to live. You need, like, because we're going to go broke and the project will end. We're not going to be able to help anyone if we go broke. That's the thing, if we go out of business. So in order to help people, in order to improve people's lives, sometimes you have to make money too. And so that is my problem with this. They're pretending like it's, I don't know, maybe it's their requirements with the sources they use. Maybe it's not their fault. Maybe they didn't make this rule up. But either way, that's my problem with this. I'm not using MedwayDB for my work just for that reason, because even though I'm not making money off of this, not making money off anything right now, but that is a philosophy that I disagree with, the philosophy that they have here. And so, but if you're going to use this for your homework, go ahead and use it by all means. You do need to cite it, depending on which one, original or 2.0 you use. You use one of these citations, which is great. And I'm sure this is a very good resource for this kind of research. A sample version can be downloaded here, and then if you want to request one of these, it is a quick, basically it is restricted access. You click on request, and then here you put your name, email, and you describe what you're trying to do with this, just so they can make sure that you're not going to make money off of it. Which is fine. Yeah, for me, from my direction, I would like to, I think for just my trials with this, I would like to see if I can see what I can do with just a spectra. And actually there is I did try to put this into an Android app as well. What I currently have is this app right here, and it's not perfect, but it plots the spectrum. So on the top we have our meeting note numbers as usual on the bottom, and the powers at the top. I'm sorry about that light, it's overhead, yeah. So, and then the bottom here is the note numbers also, but this is all the octaves added together. And it tries to calculate a score as well on how well it scores. So if we go back to our music file and play it, you can see that we have some music. Now, I'm going to fast forward a little bit. Fast forward a little bit more. So yeah, so that's that. Basically, that is also another thing I'm doing. I think basically what I would like to do is I'd like to figure out if there's a way to use these or these. If to do this mathematically, I'd like to figure out the equations for how to do this, because with deep learning you can give it, if you have a lot of data, which I don't have a lot of data. I could do some things. I could probably find a MIDI library of a bunch of MIDIs and then convert the MIDIs to MP3 and then train the model on the MP3s, and because I already have the MIDIs, that's the answer key. So I could do that, but right now that's kind of what I want to do. Is I'd like to find a mathematical model to do this with, because if I can write an equation to do it, then I think it'll be a little bit faster than deep learning. But what do I know about deep learning? So it's very robust, I guess. Yeah, and of course we could offload our processing onto the GPU as well. Now, if you have for now, I don't have the answer to this problem, so whoops. Yeah, if you have some sort of homework that requires you to do this, I would say, I guess look at these projects that these people have done, Bill 317996, or maybe find something else on GitHub or something like that. But yeah, maybe check with your professor if it's okay to use someone else's code, and if it's not okay, then probably still make your program work with their code first, but then rewrite it. And again, like, the only thing you really need to do, you can download as I said, you can download the model here and use their model. Ask your professor if it's okay to use their model file, and then write your own, this code, the estimate code. Maybe not the training.py, but because you won't need training.py, you will only need some of these. You'll just need you won't need data arrangement, you'll just need, let's see, what file is this? CFP you will need, because that's what prepares the data for the model input. You will need melody extraction.py, because that's the main function that does this. And you will need model.py or your own version of it. And you will also need some sort of main function. But really, mext this is a very simple main function. You can write your own easily. And then if you need some sort of a progress update, like I did with a progress bar here, like this progress, for example, or if you're going to write a web app or something that updates the progress, you can do that. I would add a progress listener somewhere here to the mext function, and then let's see where the mext function is defined. So it'll take the listener or a list of listeners, and it will actually give it to, it won't give it anywhere. It'll say, like, so over here, before you start, you update, you call it, you say progress is 0 out of however many, and then over here, frames is the total number of frames you're going to process. So in here, I would keep a counter of how many frames you've processed. Actually, seg_y is your counter because you append. So you do len seg_y divided by, or actually len seg_y is your completed number. Len seg_x you could use as your total number. So that way, that's your progress. So you would, in here, every time you process one of these, you would call the callback, and you would give it len seg_y divided, or not divided, but comma len seg_x. Those are the two variables. And then whatever your main code is, wherever you have that, is going to either print a progress value, or it's going to update some variable somewhere, so that if it's a web app, for instance, you can have the server update your the progress that is displayed to the user. So that's something you can do as well. Well, all right. I hope that was helpful. In particular, if you're either trying to do this particular project or understand what it does or rewrite it for yourself, or if you're trying to understand the paper that goes along with it that they link here. So that was some information. I hope that maybe I gave somebody some insight, maybe with homework or something else, but otherwise I'm just going to continue. I don't know how much time I'll have for this because I'm just super busy nowadays, but maybe someday I'll have this working, and those of you who have final projects due soon will probably already finish the final projects by the time I have time for this again, but that's okay. Just remember that Google is your friend. You can Google anything you want, and there's a lot of information. So yeah, thank you for tuning in, and I hope you have a wonderful day. Bye.